but we'll show that off anyway. So for starters, just a review, and there is a bit of notation or a convention. And I use the symmetric one. Other people don't. That's fine. There's no judgment about that. But the idea was that we had a function f of x. We'll start with x. And the function f of x is non-periodic. And the question was, this whole Fourier series trick was really useful. It let us do at least three things. It let us solve difficult differential equations. It let us intuit something about physics, especially quantum mechanics. And it let us compress complicated functions into easier ones to deal with. If only we had a version of that for non-periodic functions. And with an appropriate limit, that's true. We do have one. And it looks like this. And when you write them, especially with the symmetric convention, one on top of the other, it looks really clean. Okay, so if you want to get from function to the function's Fourier transform, you basically slap a e to the minus ikx on it and integrate over the entire real line, negative infinity to infinity. And then if you want your function back, you just do the same thing, but with a plus e to the ikx instead of minus. So that's where the name transform comes from, is that you turn your function into quote unquote k-space, and then you get your function back. And there's a little bit of notation that goes along with this. If you ever do any electrical engineering applications, you'll definitely see it, is that, so actually just call this like 2 notes, and then we'll get into actual problem solving. And I'm a pedant, that's how you end up teaching physics. So I'll put normalization in quotes. So you might see, for instance, you might see 1 over 2 pi in front of the Fourier transform, and you might see 1, which is to say no prefactor in front of the f of x. But it does the same thing. And really quickly, when we get to direct deltas, you'll see why this exists. Okay. As I said, I like the symmetric convention. So note 2 is that there's just a convention to use different names for the transformed variables. So if you are going from x, you have a function of x, then typically what you do is you transform x back and forth into k. And the meaning of this is the position. So this is, I go to some position x and then ask what the function is. And k is 2 pi over lambda, the wave number. So remember what all of these things are doing, the Fourier series and transforms are, instead of representing this function in terms of position, you're doing it in terms of wiggle, or in this case, wavelength. So this is a rephrasing of wavelength. Conversely, if you have a function of t, as you usually do in signals processing, you represent this in terms of omega. And omega is 2 pi over the period of the function. And that's the angular frequency. Okay. If you transform a function of x into a Fourier transform of omega, all you'll get from me is a dirty look, but just realize those are the conventions. Okay, so that's the thing. Question is, can we use it? Unless there are any questions about this, I'll just give you guys a problem and see how far you get. And then we'll reconvene in 5 minutes to go over it. This one has a couple of tricks and it leads us towards what we'll do next, the direct delta. Cool. All right, no news is the best news, so install that. And I will draw this as well as give you guys a representation of it. So this function is 0 everywhere along the negative x-axis, and this function goes from f0, and then it slowly decays. Well, I don't know about slowly, it exponentially decays. Depending on what that coefficient is, might be fast. And pretend I can actually draw an exponential. Jesus. How about that? That's much better. And this is one way of writing it. Actually, let's use t. Get you guys to use the right convention. So this is 0 when t is negative, and this is f0 e to the minus at when t is greater than or equal to 0, and a is got to be positive. Okay. Let's give you guys like 4 or 5 minutes to see how far you get, and then part of this is the stuff we built on last time is what do I do about these i's, and what is kind of the one trick I have for integrating, might not need it for this one, integrating things times exponentials. So why don't we reconvene? So first off, what should if I'm going to obey this good convention that everybody uses, what should I have as my variable, my independent variable of the Fourier transform? If I'm transforming something of t.
Omega.
Yeah, so we go from the time domain to the frequency domain is how the signal processing people would describe it. And then I use the symmetric convention, so 1/√2 pi t. Again, convention means that doesn't really like mean anything in and of itself. And then this would be e to the I omega t, because again, k to omega. And then we're getting rid of time, so we're transforming away the time variable, so dt. Okay, well, this function is 0 on the entire negative real axis, so that simplifies the integral. And we just get the positive real line, e to the minus at, e to the minus I omega t, dt. And then properties of exponents still work if there's an I in one of them. So this is 1/√2 pi, integral from 0 to infinity, e to the minus a plus I omega t dt. Okay. Everybody happy with that so far? Okay. You guys just integrate that and then put like a minus a plus I omega t downstairs as like the thing you get when you take an antiderivative of an exponent. Was anybody sketched out by that? Okay, you did the right thing, but you probably should be a little bit sketched out by this when you put in the limits. And I will hand wave as to why, and it turns out that it's fine. It turns out to be fine. So, oops, I forgot my f0. So we have an f0 in this function. And then I get f0 over √2 pi, and then -1 over a plus I omega, and then e to the minus a plus I omega t, and I evaluate that at infinity and 0. And then without thinking too hard, I'm just going to say like, oh, well, you know, it's an exponent, negative exponent, so at infinity it's 0, and at 0 it's 1. Anybody want to raise an objection about that, maybe possibly?
If you're treating a complex exponential as like a periodic function, then it wouldn't converge to anything at infinity, maybe. I don't know.
It's the complex value, right? Do you remember, this is going to be your best friend in this course, Euler's formula. E to the I alpha is equal to what? Cosine alpha plus I sine alpha. Complex exponentials do not die at infinity. What do complex parts of exponentials do at infinity? They wiggle back and forth in between 1 and -1 and I and -I in this case. So there's a subtle form of a limit that we're taking. It turns out you're doing the right thing, but maybe for the wrong reasons. And we'll talk a little bit at the end of this class about complex analysis, but it's on average, this does go to 0 because this part is bounded in between -1 and 1. And then this is bounded in between -I and I. So, oops, I'm in the corner of the board. I can't do anything. -I and I. Okay. So right thing, but again, right for maybe the wrong reason. And we'll get back into this. But yeah, it's 1 and 0. So, and then we have f0 over 2 pi, oops, -1, not there yet, plus I omega. And then this is 0 minus 1, which nixes the minus sign there. And I will rationalize this. So nobody cares if you rationalize square roots at this point in your lives, but it probably is a good idea to rationalize complex numbers in denominators, because what you can do is you can split this thing into its real and imaginary parts much more easily if all the complex stuff is in the numerator. So I'm going to multiply this by 1, but 1 is the complex conjugate of this. So this is the complex conjugate of that, not a plus I omega, a minus I omega, which will give us something that we can really easily just read off as complex part and non-complex part. So a plus I omega, all the gross stuff is in the numerator, and then when I crunch that out, it's, okay, this is it. This is the function. This is the Fourier transform of that weird thing. And that weird thing was an exponential, but it was also cut off. So it was cut in half with a theta function or a Heaviside function. So we'll get to that when we talk a little bit about Mathematica. And its Fourier transform turns out just to be like a really nice kind of algebraic function. So omega is our new variable. This is f of omega. And at some point in your life, you should look at a table of Fourier transforms of functions and just realize that sometimes things that look really complicated in the time domain look really simple in the frequency domain. Any questions about the mechanics of that? Okay, so I want to make 2 comments, is that we have f of omega now. If I wanted to get f of t back, like let's say some, electrical engineering student corners you someday when you're capable of being cornered in the halls of Bannon again, and says, somebody just gave me this thing f of w, and I need to turn it into a function of time. So that is just the inverse Fourier transform. And transform means you really should get the exact same thing back out. So what we should do if we did this, again, I'm using my symmetric convention because I like it. So this whole thing, and now plus I to omega t, and we want to integrate out omega, we want to get rid of that variable, should give us our original function back, right? So it's like flipping back and forth in between these 2 representations. in a practical sense, if you ever want to teach quantum mechanics to a computer, you should get a bunch of GPUs and you should do Fourier transforms, technically series, because everything's discrete on a computer, and it makes your life so much easier. So the second thing to point out is, what on earth does this mean? So our f of omega is a complex valued function. So these are the sizes of all these wiggles. And it turns out that we actually packed a lot of, it's weird because it's in the complex plane, but we actually packed a lot of actually comprehensible information in this. So if I look at this function generically, let's say I have some Fourier transform. So actually, let me just clear everything. So like, what does this mean? I got a Fourier transform, and generically, it's going to be a complex valued function. So it's going to be a real function and an imaginary function. So I'm going to have a real part, we'll call it u of omega, and then an imaginary part, I'll just pull the I out and I v of omega. All right, so this is a complex valued function. And you can interpret what that means in a relatively straightforward way if you remember the polar form of a single number. So this is spitting out a single complex number, but it's spitting out a single complex number everywhere in, for every omega. You put in an omega, I have to tell you what the complex function is. So what you can do, honestly, is you can interpret this in the following way, is I can take the modulus of the function, which would be u squared plus v squared, all in a square root, and then I can look at the arg of that, which is to say f of omega is equal to u of omega squared plus v of omega squared. That's just the modulus. They're functions, but it's just a complex number. And then arg of f of omega is equal to arctan v of omega over u of omega, right? A point in the complex plane. So this is f of omega. And I can interpret this as some angle and some length. And what this is in some sense is, again, Euler's formula, it's going to be your best friend for about half of this class, is this is a wiggle, right? So this is sine, well, cosine plus I sine. I'm just going to do dot, dot, dot instead of writing the modulus of the complex number of the function. And sine of dot, dot, dot. So this is still a Fourier sort of thing. Like this is a wiggle. This is cosines and sines. And then this is a coefficient. So the thing that you get out, it might be spooky at first because maybe you haven't spent too much time with complex valued functions, but all you're doing is representing a point on the complex plane. It's just the point itself is a function of your input, so your omega. So any questions about that? I'm going to really quickly go over a couple of properties of Fourier transforms, and there are many, many more. And then try to talk about one of the properties that we'd like it to have and use that as a launching point to talk about a really awesome function. So some of them are, it kind of sounds grandiose, but these are just properties of integrals in general. So any integral transformation, integrals are linear, so the Fourier transform is linear. So what we're going to do, just so I can have a clean notation, is we're going to define big, cool, scripty f is the act of taking the Fourier transform. So this is a function on functions, if you will, a functional. And what's true is f of k is linear. So if we have two functions added together that we put in, we can take the Fourier transforms independently. And of course, you can sub in t and omega. And that's not exotic, that's just, it's an integral transform. If I integrate two functions added together, I can just integrate them separately. Okay, this is a new and cool one. This is a transformation property. So if I take, and in fact, we got close to proving this, you can see it in the example we did. If I shift a function, plus or minus, doesn't matter, by some amount b, I get this translation prefactor. Oops. And this is actually really easily provable. It's, if you think about where that x shows up in the Fourier transform, it shows upstairs in an exponential, and then you can just factor this out, and it comes right out of the x integral. So there's a transformation property. And then we'll just say many more. Reason not even to list them is maybe at some point you'll have to worry about convolution. If you need it, just prove one of these and you kind of get the style of the proofs. Okay, this is a thing that we would love to prove, is that, remember our great analogy where what we were saying in some sense is, hey, these vectors are, you know, geometric objects that live in space. We can represent them with a variety of different bases suited to our needs. And functions are kind of like vectors. So what we're really doing with the Fourier series is we're representing them in terms of these basis functions. And we had, you know, 2 over t sine 2 pi k tx, and then maybe I had another basis vector 2 pi over t sine j tx. And what happens if I multiplied these together and I integrated over one period?
It depends on j and k.
Exactly. So we chose the root 2 over t to make these normalized. And what I end up in general with is everyone's favorite symbol, the Kronecker delta. Okay, what took the role? And we did it in 2 steps. We did it, you know, in some sense, what we're saying is we have a basis, right? So these sines and cosines form a basis. When I overlap a sine with a cosine, it vanishes. But the sines themselves and the cosines themselves, Kronecker delta. So we're representing the function in a basis, so the basis itself needs to satisfy basis things. So we did this in 2 steps. We did this first by making the exponential form of the Fourier series, and then we took an appropriate limit to get a Fourier transform. So I'm just going to call it FD for Fourier transform at this point. And you can ask the following question: is these exponentials Do they form a basis? And, you know, it's an important question in a sense, because if it's a basis, then we know all of this linear algebra stuff. We know that we can uniquely and completely represent a function in this new basis. So what that boils down to essentially is this, is if I take one of these things, e to the I, you know, the 1/2 pi turns out to be irrelevant, as I've said many times, e to the I k1x, we'll call this like basis vector 1, and then basis vector 2, also 1/√2 pi e to the k2x. Okay, thing we haven't talked about too much yet is that once we go into complex numbers, I need to take the complex conjugate when I multiply two things in an inner product. So just believe me for now when I say that this actually needs to be a plus, because we're taking the inverse transform. Okay, so this, and I multiply them together, and I integrate over the entire real line, and I want to get rid of x. So what do you think this is going to be? Don't think, just blurt out an answer.
Also the Kronecker delta.
Be super cool if this is the Kronecker delta symbol. Okay, let's try it. And remember that K1 and K2 are any real number. So they can be anything in between negative infinity and infinity, including, you know, pi to the e power or something like that. So let's do K1 equals K2 first. Let's get the integral over the entire real line, and then this 1/2 pi, just put that out there. And then I get, what is the plus I? K2 minus K1 x dx. Okay, and when K2 equals K1, what do I get in the argument of the exponential? Get e to the I times 0 times x dx, which I times 0 is still 0. So this whole thing becomes 1. What is that integral? So I'm integrating 1 from negative infinity to infinity. So that's infinity. This is not a good start. We wanted 1. Okay, and then we'll try this again with k not equal, k1 not equal k2. Okay, well that doesn't go away, but it becomes this thing, we'll just define it, you know, delta k. And aha, that subtlety that showed up in the limit will come back to haunt us. So this is something that looks like delta k, which is not 0, x dx. Okay, what is this limit? So what does Euler's formula say about this?
On both ends, it would continue to oscillate.
Yeah, so it does the exact same thing that we kind of glossed over in that Fourier transform that we started today with. And cosine, so the cosine part, you're like, okay, well, there's a name for this called the Abel limit, where it spends all its time in between +1 and -1, and it does so symmetrically. This might seem super shady, but you can define the limit to be 0. And then likewise, this part spends all its time in between I and minus I, because the I out in front. And you can say on average, it's 0I. You can get a little bit more into this, but for all intents and purposes, this is 0. The whole point is that this is not really what you wanted. So we would have loved to have a Kronecker delta symbol, right? Where it's 1 when they're equal and it's 0 when they're not. We kind of have the 0 based on at least, kind of redefining what we mean by limits. Don't like it. So this is at least on average. So we can set averages to 0. Does anybody know what this actually is? It's probably a function, and you should use function maybe in some air quotes that you've seen before, maybe probably in modern physics.
In differential equations, we talked about the Dirac delta symbol.
Yes. So
Okay.
this is, the Kronecker delta is for finite stuff. For infinite things, it generalizes into a thing called the Dirac delta function. And so that is, let me just, I'm going to try splitting up the videos a bit because we're going to use the Dirac delta function for more than this. So give me 1 second.